Welcome back to another problem. Let's begin. The pin at joint Q is constrained to move in a circular path of radius rho is equal to 0.08 meters at a constant rate of alpha dot is equal to 48 radians per second. The slotted arm rotates accordingly about its base. Determine r dot, r double dot, and theta double dot of the slotted arm when alpha reaches an angle of 33 degrees. So given this problem, I can expect to use the polar coordinate system. However, I have a ton of unknowns. I essentially don't know any of them. So I'm not really sure how to proceed, but I can go ahead and write out my givens. And I normally find that writing out all your givens is a very helpful tip and can really help you get started. And so given that my system, my system in general, I can see a triangle formed between theta and alpha. And so if I recall my law of cosines, it might be really helpful if I have that triangle defined, if I can then further define all my sides and all my angles within it, because maybe one of those values would be helpful. So using the law of cosines, I can calculate that r is 0.2616 meters. Okay, now that we have that, we can do the law of sines to calculate theta as another value. And you can see me here drawing out the coordinate system, and I can track the joint Q as it travels in that circular path. And since velocity is always going to be tangent to that path, we know that the direction Q points to when alpha is 33 degrees. Likewise, since the velocity is due to the angular velocity of the crank arm, we can directly calculate it as rho is equal to alpha dot. And doing so yields 3.84 meters per second. All right, great. So we got we got a few values calculated so far. Block that section off and continue. Copy our coordinate system over. And yeah, so now we have our new diagram. Now remember, we want to really keep our coordinate systems succinct and clear. And you always want to remember that your coordinate system, they have to be two linearly independent vectors. So you always got to remember that your two axes have to be perpendicular to one another. So that's an important thing to remember, because we're going to use 90 minus some values here shortly. And so if I plug in my values for alpha and theta, I can calculate this unknown parameter gamma, which exists between the tangential and radial coordinate systems that I drew out. And doing so yields 47.412 degrees. Using that, we can then use our concept of the velocity triangle to get the different values for velocity in different coordinate systems. So specifically, we know gamma and we know the tangential velocity, so we can get the radial and or the velocity in the radial and theta directions respectively, just using some simple trigonometry. And likewise, because we know that, we also know it's going to be equal to r theta dot by the definition of the velocity in the theta direction. And thus we can calculate theta dot is equal to 10.807 radians per second. Likewise, we can do the same thing for the velocity in the radial direction, and because that is purely just going to be r dot, we can calculate it as being 2.598 meters per second. Okay, moving right along. We're going to do the same procedure one more time for the acceleration. Again, we want to make sure that we have a linear independence amongst our basis vectors that describe our coordinate system. And again, this is perhaps a muddy point, because you can have a lot of coordinate systems that can maybe muddle your diagram, but you just want to really keep that straight. And so using our normal and tangential coordinate system, we know that the normal acceleration is going to be that tangential velocity squared, all divided by the radius of curvature, all of which we know, so we will just plug in those values and we can calculate. Then using our concept of the acceleration triangle, we can write in our values for AR of Q, a theta of Q, and a normal of Q. And again, since we were very clear and succinct with our coordinate system and our picture that we drew, we can see that that angle between the radial and normal components of the acceleration is alpha plus theta. Using simple trigonometry, we can write out an expression with the sine of the angle to calculate the acceleration in the theta direction. And note that we have that negative sign because it actually points in the negative direction with respect to how we define our coordinate system in the acceleration diagram. Thus, we can calculate the second derivative of theta, which is going to be theta double dot, and we calculate that as negative 691.46 radians per second squared. Likewise, we'll do the same story for cosine, which will give us the acceleration in the radial direction, and we will just calculate that straight up as being about 135, and then we can use that expression to get our relationship with r double dot, which we then can calculate. And yeah, that was a good problem, and I hope it was helpful.